Electrostatics, Electric Boundary Conditions, Series on Electromagnetic Field Theory, lecture number 1.70. Boundary means end. Boundary means termination of a medium. Not only that, it is also beginning or starting of another medium. The fields on one side of the boundary are related to the fields on the other side. These relations are called boundary conditions. In the present session, our focus is on the electric field boundary conditions. Boundary is end of one medium, it is beginning of other. Interface is an imaginary surface between the two media. Let us suppose this is one medium, this is another medium, medium 1, medium 2. This is boundary of one medium. It is boundary of other medium also, medium 2 also. Interface is an imaginary surface. This is an imaginary surface where these two media meet each other. It is possible to have set of relations connecting field quantities on one side of the interface boundary with those of the other side. These are called boundary conditions. These are highly useful to find quickly and easily the field on one side of the interface when the field on the other side is known. These are two. One relates tangential electric field that connects normal displacement density across the interface or boundary. First, let us see tangential components. Tangential component of electric field E is continuous, assuming same value on both sides of the interface between two media, regardless of charge densities on the interface. Mathematically, ET1, E means electric field intensity, T means tangential, 1 means in medium 1. Similarly, ET, electric field intensity, tangential component in medium 2. The tangential components remain same. What does it mean? This is the interface. This is medium 1, let us say. This is medium 2. Let us say this is 2. Let us also suppose everywhere here electric field is there. Now you consider electric field component in medium 2 parallel to the interface. This one can designate it as ET2. Similarly, consider near to the interface or near to the boundary electric field in medium 1, and let us suppose the parallel component of it on interface is ET1. He says ET1 equal to ET2. Charge may be there over the interface, charge may be absent, it doesn't matter. Irrespective of what is happening, what is existing over the interface, tangential components are same, remains the same. Now, if its application, its utility, its use for us is, suppose you know ET1, it is available. Using this condition, you can say what is ET2. You need not calculate ET2 going for Coulomb's law or Gauss law. Simply by this relation, by bringing forth this relation into your mind, just simply you can, without any calculation, ET2 can be found. Of course, ET1 must be known to you. However, continuity of tangentially implies discontinuity in tangential displacement density across the interface as D equal to epsilon E. Here, epsilon assumes different values for different media. ET1 is ET2. These are two different media. So epsilon 1, let us say, permittivity medium 1 is epsilon 1, permittivity medium 2 is epsilon 2. These are two different media. So epsilon 1 is different from epsilon 2. Therefore, DT1, which is epsilon 1 ET1, must be becomes different from epsilon 2 ET2, which is DT2. So DT1 is different from DT2. That's what is there. The ratio of tangential displacement densities across the interface is equal to ratio of permittivity values of the medium. Mathematically, the same thing is put in this form. ET1 is DT1 by epsilon 1. ET2 is DT2 by epsilon 1. So therefore, DT1 by DT2 is epsilon 1 by epsilon 2. So across the interface of any two different media, the tangential component of displacement densities are always discontinuous. Now come to normal component. The normal component of displacement density D is continuous, assuming same value on both sides of the interface, except when the surface charge sigma is present. Sigma already it is introduced. It is charge per unit area. Units are coulombs per meter square. In such case, in the presence of interface charge over the interface, discontinuity happens and it is equal to surface charge density. Mathematically, dN1 equal to dN2. This is the condition that is valid in the absence of surface charge. In the presence of surface charge, dN1 minus dN2 becomes sigma. In either case, it implies that a normal component of electric field intensity E is discontinuous across the interface. In the absence of surface charge, the ratio of normal components of electric field intensities is inversely proportional to ratio of permittivity values. See, you consider this situation. Absence of surface charge. dN1 is epsilon 1 En1, dN2 is epsilon 2 En2. So ratio E1 by En1 by En2 becomes epsilon 2 by epsilon 1. Okay. So this is as far as normal components are concerned. Now tangential component. One condition on tangential component, one condition on normal component of electric field. These two together, they are called electric field boundary conditions. Now how these two conditions, tangential condition, normal condition, how these two are derived, here is shown. Applying EMF equation, this is called EMF equation, closed line integral E dot dl equal to 0. This is for static fields. Static fields, E dot dl equal to 0. Using this equation, one can find condition pertaining to tangential components. And applying displacement equation over Gaussian pillbox located over the boundary, this equation. This is Gauss law in integral form. By applying this equation, one can find normal boundary condition. Applying EMF equation around a rectangular loop. Here a rectangular loop is considered located over the boundary. Relation connecting tangential electric fields can be attained. Using this law, normal electric fields can be, condition connecting normal electric fields can be obtained. You see here application of EMF equation requires closed integration over a closed path. The closed path that is selected here is a rectangular loop. Here is shown rectangular loop. So integration is performed over a rectangular loop. Notice this rectangular loop is placed half of it above xy plane, half of it below xy plane, and it is normal to xy plane. The loop is normal to xy plane, or it is parallel to z-axis. Shorter sides are parallel to z-axis, longer sides are parallel to y-axis. Half of it is below xy plane, half of it is above xy plane. Above xy plane, medium 1 is there. Below xy plane, medium 2 is there. Medium 1 is characterized by epsilon 1 P1. P1 is polarization. Epsilon 2 P2. P stands for polarization. Epsilon 2 P2 pertains to medium 2. Epsilon 1 P1 pertains to medium. Now, applying this equation over this loop, rectangular loop, tangential component, boundary condition relations can be obtained. To obtain normal component boundary relations, what we do is we consider a Gaussian pillbox. It is shown here. Half of the pillbox is above xy plane, remaining half is below xy plane. Above xy plane, medium 1, below xy plane, medium 2 is there. Now d dot dA over closed surface. This surface, Gaussian surface, it is used in evaluating this integral. That integral results in normal boundary conditions. So detailed application is shown here. Consider an interface lying in xy plane of two dielectrics, one above other having permittivity values epsilon 1, epsilon 2 occupying regions 1 and 2 respectively. Now by applying EMF equation around a closed rectangular path encompassing a part of the interface, E dot dl becomes 0 means E dot dl means closed line integral. Top side, you have to perform integration over top side, right side, bottom side, left side. It is equal to 0. Now as the width of the loop delta z tends to 0, integrals over left and right sides become 0, so resulting it results in Ey1 delta y minus Ey2 delta y equal to 0. Therefore Ey1 equal to Ey2. But y1, y2, these are tangential components. Ey1 means it is parallel to the interface. As y components are parallel to the interface, it can be inferred that tangential electric field is continuous across the boundary interface. Et1 equal to Et2. This is the way tangential boundary condition is derived or arrived at. This is the proof. Of course, it can be converted in terms of displacement also. It results in dt1 by dt2 equal to epsilon 1 by epsilon 2. To derive the condition on normal components, consider a small Gaussian pillbox, as already mentioned, with a cross-sectional area A enclosing the interface. By applying Gauss law over pillbox results in, this is closed surface integral. It means you have to perform over all the faces. We have top face, we have bottom face, we have side face, curved face. Of course, it is equal equal to rho d2. Q enclosed is rho d2. If charge is there over the interface with density rho, then rho is there. Then net charge enclosed by the pillbox becomes Q enclosed is rho. See here, rho is volume charge density. It becomes rho delta Z delta A. As the thickness of box tends to 0, side wall area, consequently the flux through the side wall becomes 0. Therefore, dNA delta A minus dN2 delta A is equal to rho delta Z delta A, which is equal to sigma delta A. Hence, dN1 minus dN2 is sigma. Here on small correction, cross-sectional area is delta A. Let us say cross-sectional area is delta A. Then dN1 delta A minus dN2 delta A. It is rho dZ delta A. Rho dZ is actually, it gives you surface charge density. Surface charge density. So ultimately you are getting dN1 minus dN2 is sigma. The tangential as well as normal component polarizations of the interfacing media can also be connected. See, so far we have considered the insulating media like space, free space or air. Now one of the media or both of the media are dielectrics. Let us say dielectrics carrying certain polarization are capable of polarization. Then in such case we can express these two conditions: tangential continuity of tangential component, continuity or discontinuity of normal components. We can express in terms of polarization also. How? ET1 equal to ET2. This is the actual condition. It is applicable, universal, whether it is dielectric or non-dielectric, or whether it is conductor, ordinary conductor, perfect conductor. It doesn't matter. It is always true. ET1 equal to ET2 is always true. dN1 minus dN2 equal to sigma. It is always true. It doesn't depend upon the type of media. If one or both of the media happens to be polarized dielectrics, then one can convert this relation into relation which is in terms of polarization. How? ET1 can be replaced by PT1 by epsilon naught xi E1. ET2 can be replaced by PT2 by epsilon naught xi E2. Here xi E is susceptibility, electric susceptibility. This your understanding grows if you know polarization is epsilon naught xi E. This is the relation between polarization and field intensity. You have this relation, then within no time you can find out PT2 is xi E2 by xi E1 PT1. When it comes to normal component, this is the universal general relation. Now first convert it into electric fields, field intensity, En1, En2, and then En1, En2 can be replaced by polarization using P equal to epsilon naught xi E. Ultimately, Pn2 is given by a slightly lengthier complex relation. Here whatever all we discussed, they are placed here. Tangential E, tangential electric fields are continuous. Tangential D is are given by this formula we have already derived. Normal E, normal D. When we consider dielectric conductor interface, listen, if one of the media happens to be a conductor, let us say this is one conductor, one media, this is second media. Now this is a perfect conductor. Inside perfect conductor, field cannot exist. So tangential electric field here it is 0 in conductor. Therefore tangential electric field, it must be 0 here also, here also. Therefore tangential components are zeros. ET1 equal to ET2 equal to 0. This is the story. Similarly, DT1 equal to D2 also becomes 0. So this is specific case, dielectric conductor interface. One of the media is conductor. Okay. Now there is a law, refraction law of displacement. Normally refraction, reflection, these are all phenomena associated with wave. In static fields, no wave exists. Electric field is not a wave, but static electric field is not wave phenomena. So refraction is something foreign, something alien to static fields, but still this term is used, refraction law of displacement. The reason is this law in form, it is similar to Snell's law Snell's law of refraction. Sin I by sin R equal to mu, which is refractive index. It is similar. That's why it is called refraction law. Right. Snell's law of refraction connects refractive indices of media with angles of incidence and refraction. Similarly, values of permittivity of two contiguous media can be connected through angles. Tan theta 1 by tan theta 2 equal to epsilon 1 by epsilon 2. Here it is illustrated. See, this is interface. Here is medium 2, here is medium 1. Now you consider D here on one side. D. So it is D2 because the point is in medium 2. Consider D also on the other side. It is D1. This is D1. This is D2. Now you sketch it. D1 may be like this. D2 may be like this. So D1, D2. D1 makes certain angle to the normal. D2 also makes certain angle with the normal to the interface. Or we call them theta 1 and theta 2. You can also see this D1 makes certain angle with the interface. D2 also makes certain angle with the interface. These two angles are usually different. You can see they are different actually. So here theta 1 is shown as angle D1 makes with normal. Here D2 is shown as theta 2 is shown as angle D2 makes with the normal. It can be shown tan theta 1 by tan theta 2 is epsilon 1 by epsilon 2. Using this law, it is possible to estimate field intensity in one medium from the field in the neighboring medium. It can be observed that D is larger in the medium of larger permittivity value, but E is larger in the medium of smaller permittivity. So this law, derivation of this law is quite simple, quite easy. It can be derived from continuity of tangential components and continuity of normal components. Combining those two, one can obtain this relation. As it is similar to Snell's law, form-wise, appearance-wise, it is called refraction law. But don't think that there is any wave here. This law is named as refraction law of displacement. This is what I want to share with you for now. Before concluding the session, let me recollect. There are two boundary conditions, electric boundary conditions. One is on tangential components, or one connects tangential electric field intensity. Another is on normal components. To be precise, it connects normal displacement density across the interface. These are useful in finding field on one side of the interface when the field on the other side is available. Enough.